Billions of years in the past, when Earth was new, there were no rocks. Earth was a burning hot gooey ball of melted minerals and metals called magma. Eventually, as heat drifted into space, Earth's surface cooled. A thin crust of rock formed over it, like ice over a lake in winter.
The heart of the Earth, its inner core, is a solid ball of iron and nickel. Here the pressure is so high it never melts, despite the intense heat of 3,700 degrees Celsius. The outer core is under less pressure, so it is molten. This is enclosed by a deep layer of hot rocks called silicates. This is the mantle, and it's 3,000 kilometers thick. The surface is hard and forms a solid crust. If the Earth was a peach, this crust would be as thin as its skin. But the Earth's crust is cracked and brittle, like an eggshell. It's made up of several segments called tectonic plates. The plates float on the dense mantle. Scientists believe that the immense energy of the Earth's inner heat sets up convection currents in these rocks, which move the crustal plates about, but very, very slowly.
I mean, let me just give you an example of this thick, viscous flow stuff. If you take a glass of honey and put it in a pot of warm water, such that it's being heated at the bottom and cooled at the top, if you just look at it in real time, it doesn't look like it's moving.
So as you can see, the honey looks remarkably static. And then below it, I've added a heat source, which is just some water, hot water. So what does our static honey look like in time lapse?
But if you add a little more time into that, then all of a sudden you can very easily see the convection currents. And those are the convection currents which are moving around the tectonic plates.
And these days we directly track that motion, with millimeter precision, from space. The common simplified explanation for why tectonic plates are moving is that they're carried along on currents in the upper mantle.
Some plates are moving apart. Some move towards each other. Other plates just slide past one another.
Converging currents drive plates into each other, diverging currents pull them apart. This is mostly true. Hot mantle rock rises from the core and moves along under the crust until it grows cool and heavy and sinks back down again. But the plates aren't just passively riding these currents around like a bunch of suitcases at the baggage claim. They can't be, because some of the plates are moving faster than the currents underneath them. For example, the Nazca Plate, a chunk of ocean crust off the west coast of South America, is cruising eastward at about 10 centimeters per year, while the mantle underneath it oozes along at just 5. Neither tectonic plates nor luggage can move faster than the belts they're riding on unless something else is helping to push or pull them along. And some of Earth's plates, it turns out, are pulling themselves. When an ocean plate collides with another ocean plate, or a plate bearing the thick crust of continental land masses, the thinner of the two plates bends and slides under the other. As the edge of the sea floor sinks into the mantle, it pulls on the plate behind it, the same way a chain dangling further and further off a table will eventually start to slide. The bigger the sunken portion of the plate becomes, the harder it pulls and the faster the remaining plate behind it moves. What's more, these chunks of seafloor are actually helping to drive convection in the mantle beneath them. Sunken slabs of ocean crust block flowing rock from moving further sideways, forcing it to turn downwards and sink. And eventually those slabs get too heavy and break off, plunging slowly toward the core and creating a suction force that pulls mantle material along behind them.
The plates are moving very, very slowly, less than 5 centimeters a year. But over time, this has added up. In 1963, Icelandic fishermen spotted plumes of ash, steam and lava shooting out of the sea. Almost overnight, a new island emerged. Lava poured out of the earth. The eruptions didn't stop until 4 years later. Within months, birds began to visit and plants grew. But what had happened? At the bottom of the ocean, 2 plates of continental crust had slowly moved apart. Molten rock called magma, lying below the plates, oozed up through the cracks. When it reached the surface, the magma cooled and solidified, forming lava. This gradually built up until it broke through the ocean surface to form an island. A ridge of lava and mountains has been formed where the two plates have moved apart. This runs down the middle of the Atlantic Ocean.
French geologist Jacques Malavier builds sand models that mimic the formation of mountain belts and allow scientists to study this complex process.
In order for an experiment that runs for only a few minutes but represents natural phenomena that happen over many tens of millions of years, we have to choose a material whose deformation behavior does not depend on time. Sand is a very good material for simulating rock deformation. In the experiment, the different stratigraphic layers which represent the sediments and the continental crust have different mechanical properties. We mix the sand grains with a finer powder, which increases the sand's resistance to deformation. Thus, we have heterogeneous material made up of more resistant layers and less resistant layers.
Mountain belts are created when continents collide.
These mountains are caused by the collision of two plates of continental crust. They're called fold mountains because the layers of different rocks within the Earth's crust, the strata, are folded and bent.
In this experiment, we see two continents separated by an ocean. Now watch what happens as the plates converge. As one plate subducts or dives beneath the other, the ocean basin closes. The continental crust, which is lighter than oceanic crust, cannot be subducted. Instead, as the continents collide, the crust thickens and is forced up. Note how the sand is folded and faulted. We see similar structures in the rocks in mountains. One important factor not accounted for in this model is erosion. Erosion exposes the deformed rocks that were once deeply buried in the mountain belt.
Over time, erosion of the layers can occur at different rates, producing characteristic jagged rock formations.
The green sand represents the rocks of the ocean basin. Note that it's been trapped between the two continents, marking their original boundary. These too we see in mountain belts. The sand model allows us to compress time and space and simulates the internal structure of mountains.
There are two kinds of crust. Continental crust forms the great landmasses of the world. This is thick. These rocks are made of ancient lightweight substances like granite. Some were formed almost 4,000 million years ago. Oceanic crust, which lies under the planet's great oceans, is much thinner. Oceanic rocks like basalt are heavy and much younger, 1/20th the age of continental rock. Volcanoes like Merapi in Indonesia are caused by the collision of oceanic and continental plates along what is known as a destructive margin. Over millions of years, heavier oceanic plate is being forced down under the lighter continental plate, creating a trench. Carrying water and debris with it, the oceanic plate breaks up under immense pressure. As it's forced down, it gets hotter and hotter, due to friction and because the temperature rises rapidly towards the Earth's center. Eventually it melts, and the molten magma rises to form volcanoes some distance from the trench. Sometimes a row of these volcanoes can form an island, like Java. Millions of years of eruptions have made the country very mountainous and fertile. These volcanoes release ash and rocks that break down quickly into soil, producing new supplies of the minerals plants use to grow. This makes the land very productive. So what happens within the volcano to make it erupt? Molten magma from below the Earth's crust pushes up into the mountain. This causes tremors, and tiltmeters can actually detect how much the mountain is bulging as it fills with magma. This is thick, like porridge, and when it reaches the surface, it solidifies into a hot, crumbly plug. Pressure on the magma builds up, and bits fall off all the time. The plug, or dome, gets too big and top-heavy. Eventually, it's forced apart.
The liquid rock matter that we see coming out from volcanoes is called magma. When this magma reaches the Earth's surface, it is known as lava. The cooling and the solidification of lava at the Earth's surface result in the formation of extrusive igneous rocks. They are also known as volcanic rocks. The cooling and the solidification of magma at a depth within the Earth's crust result in the formation of intrusive igneous rocks. So we have learned that igneous rocks are of two types: extrusive igneous rocks and intrusive igneous rocks. It is interesting to know that igneous rocks were the first to be formed.
Some of that original rock formed more than 3 billion years ago, as Earth was cooling off.
Earth's surface cooled. A thin crust of rock formed over it, like ice over a lake in winter. This crust, made of minerals and metals cooled from red-hot magma, was igneous rock. Igneous rock occurs in many forms. They vary according to the kind of minerals and metals they're made of and how fast they cooled. Granite cooled slowly underground over thousands of years. Obsidian, which looks like black glass, cooled quickly, as did pumice, which floats in water. Though varied, all igneous rocks hardened directly from magma. The second rock of our story is sedimentary rock. Sedimentary rock develops through a long process that starts with weathering and ends with lithification. Weathering breaks down rocks on Earth's surface through mechanical, chemical, and biological forces. In mechanical weathering, heat, cold, ice, wind-blown sand, and falls slowly crack and wear down rocks. In chemical weathering, rock dissolves in rainwater, which is slightly acid. In biological weathering, plant roots both crack and dissolve rocks. Weathering occurs slowly, but old gravestones in cemeteries show what can happen to exposed rock. Over time, even huge mountains weather bit by bit into sand, dust, clay, and minerals dissolved in water and disappear. 200 million years ago, the Appalachian Mountains were several times their present height. Where do the mountains go? They get carried away through erosion. Wind, and especially water, moves each bit of mountain rock downhill. Eventually, eroded rock fills up nearby valleys or gets carried away in a river out to sea.
Where rivers flow into the sea, the land either pokes out or bends inward. So why do they have innies and outies? Well,
An example would be
during the last ice age, sea levels fell by over 120 meters, and rivers cut deeper and deeper valleys to reach the falling seas. Then, about 18,000 years ago, warming temperatures began to melt the ice, and the now rising seas flooded river valleys around the world, creating giant estuaries and giving us the innie-riddled coastlines we have today. But when the steady landward march of the seas finally began to slow about 7,000 years ago, the coastlines around the mouths of some rivers began to gain back some ground. The key factor was the sediments that rivers drop as their currents slow at the entrance to the sea. Where the sediment supply was big enough and the ocean was calm enough, the dropped dirt piled up, eventually forming new land that both lengthened the river and divided it in two. Dirt would continue to drop out and build up at the mouths of both channels, splitting the river again and again and again, creating a new lobe of land advancing slowly into the sea.
Wherever they settle, sediments accumulate in layers. In oceans, sediment layers may grow higher than our tallest mountains. Upper sediment layers press down on lower ones. This helps lithification, the process that turns sediments into stone. Sometimes layers get squeezed so hard, sediment grains get shoved into one another and lock into place. Other times, water evaporates from a layer and leaves behind minerals that glue together the tightly packed grains. Either way, what was once sand, mud, or gravel becomes sedimentary rock. Depending on how it formed, sedimentary rock may be quite hard, or rather weak and crumbly. Sedimentary rock may not stay forever where it's settled. Strong forces within Earth sometimes push up rock from the bottom of a valley or an ocean into spectacular peaks and long mountain chains. Once sedimentary rock, or any other kind of rock, gets uplifted, it undergoes another cycle of weathering. This story's third chapter tells about metamorphic rock. Metamorphic means changed. Metamorphic rock may start as igneous, sedimentary, or even another metamorphic rock, but then somewhere deep underground gets changed by heat and pressure.
There are two types of metamorphism that occur in nature. The first type is called contact metamorphism, and the second is called regional metamorphism. And so I'm going to show you how contact metamorphism works. The reason it's called contact is because it involves existing rocks coming into contact with really intense heat, which is generally provided by lava or magma. So imagine that one day an intrusion of magma forces its way up through these layers of rock. Now, all of the existing rock are going to be burned by the heat of the magma. So all along the edge of this magma, shown here in orange, you're going to have rocks that have been burned by the heat of the magma. That burning causes them to change or metamorphosize into something new. So anywhere you see the orange, you're going to have some metamorphic rock. This is caused primarily by heat. But let's talk about the second type, regional metamorphism. Now this one is going to be more from pressure. So let's imagine that I have a plate boundary here, a fault, a crack, and that these two plates are coming together. So it's a convergent plate boundary. Well, as you can imagine, in the middle here, there's going to be immense pressure, and that pressure can cause the rocks trapped in the middle to become metamorphosized. So all along this boundary, you'll find metamorphic rocks. Again, this is different from contact in that it's not so much about the heat, it's more about the pressure. Let's take a look at what we see here. This is a typical progression of metamorphism that occurs. Starting with the sedimentary rock shale, if you add heat and pressure, it will metamorphosize to slate. If you add more heat and pressure, it will become phyllite, more, and it will become schist, even more, and it will become the metamorphic rock gneiss. Take a look at that gneiss sample down there. You'll notice it has bands of minerals. That's a result of the intense pressure.
What once were flecks of black minerals are now stripes or layers of it.
Now, if you were to take gneiss and add additional heat and pressure, it would likely melt into magma or lava, and then it would become an igneous rock. So gneiss is generally the extent of metamorphism that we see.
Even the beauty of metamorphic rock cannot protect it from the forces of weathering. If uncovered, it too will eventually fall as sediments. It starts long ago and continues today, with lots of fire and ice, mountain peaks and ocean waves, and more time than we can imagine. So these are three rocks: igneous, sedimentary, and metamorphic. some are as old as can be, others as new as today. In a way, they're all the same, because they all started as hardened magma. But still, each is different because rocks can change.
Over long periods of time into rocks of another type. For instance, igneous rocks can be broken down through weathering, and the pieces can form sedimentary rocks. Igneous rocks can also change into metamorphic rocks when exposed to heat and pressure that change them but don't melt them completely. If exposed to high enough heat, they can melt back into magma to form new igneous rocks. Sedimentary rocks can break down through weathering to form new sedimentary rocks. They can also be transformed into metamorphic rocks through the action of heat and pressure. If they get hot enough, they can melt into magma to form igneous rocks. Metamorphic rocks can break down to form sedimentary rocks. They can also be converted into different metamorphic rocks when exposed to heat and pressure. Like igneous and sedimentary rocks, metamorphic rocks can melt into magma to form new igneous rocks. As you can see, the interactions between the three main rock types can take several different paths.